Hi, and welcome to problem session for Lecture 9. Here we're going to discuss continuous distributions and finish up the part on probability. So just like in the previous problem session, I want to begin by discussing a little bit what they're used for. Again, because in the book there's a question about what you might want to, what political process you might think could be drawn from distributions like the normal or log normal, exponential, Pareto, gamma, or variable. Again, there are many possible answers for this, but I might think of a couple. Distribution of any personal characteristic might be normal in the population. A lot of times, because the normal distribution has special properties, the central limit theorem, you see a lot of distributions that are distributed, a lot of characteristics distributed across the population, be distributed normally. Some things are fit to be the normal distribution, SATs, IQ, these are supposed to be fit to be a normal distribution, but a lot of characteristics that are personal characteristics are distributed normally across the population. So in some cases, if you condense preferences down to a left-right scale, you also see normal distributions across the population. Logistic distribution could model the latent propensity to vote. So oftentimes, political scientists use logistic distributions to model latent propensities, to take some dichotomous action, like vote or not vote. Then again, the logistic distribution does carry with it a bunch of assumptions on the thickness of the tails of the distribution. Remember, the normal distribution might look like that, whereas the logistic might have thicker tails. That's horrible, so I'm going to write that immediately. But the point is, there's more of a chance of getting outliers in a logistic distribution than a normal distribution. I'm saying logistic too fast. Logistic distribution than a normal distribution. So you might have to see it. So maybe it's useful, maybe it's not, but it often is used anyway. An exponential distribution might treat failures. So we talk about their constant failure rate or whatever, but it might treat failure as a conflict ending. Right, so instead of a failure being a bad thing, a failure here for an exponential distribution, these are duration distributions, they measure the duration of events. Instead of a failure being a bad thing, it could be the ending of a conflict. So you could view conflicts ending as distributed according to some exponential distribution, assuming a constant rate of conflicts ending with no new ones starting. So these are possible ways you could be observing these different distributions, and of course there are many more. This just gives you a sample. Okay. Now again, like the previous problem session, I'm going to go through and show how you can use these things to compute. Unlike for discrete distributions, you know that you can't actually assign a meaning to a probability. You can't say that a probability that x equals some little x, some random variable x equals some value little x in a continuous distribution, because that's always going to be 0. A continuous distribution has probabilities assigned across the entire distribution continuously, and therefore if you integrate it to 1, you have to make sure that the chance of being at a given point is always 0. Instead, you have to figure out the probability of being in any region of space. This is stuff we discussed in the lectures and it's in the book as well. However, you can still use them to figure out things like expected values. So we can talk about, say, the mean. Let's find the mean of the exponential distribution now as an example. Well, for a continuous distribution, the expected value is equal to x. So this is just like an analogy to the previous case. X times the PDF, the integral this time, from negative infinity to infinity. This is a definite integral. So now we can fit it to any particular PDF. The PDF for the exponential distribution looks like this, and it's defined from 0 to infinity, where mu here is the mean, so we should get mu out, and we will, but we'll see how to do it. So we immediately make this from 0 to infinity. We put the 1 minus mu out front, and then we have x e to the negative x over mu dx. Now I'm going to make a quick change in variable to u equals x over mu. That means du equals 1 over mu dx. So dx equals mu du. We can change variables then, and we therefore get this. 1 over mu. There's a mu from this du, and there's another mu up here because x equals mu u. Maybe I shouldn't have used u. Anyway, too late now. So that's a u. So that's 2 mu, so there's a mu squared out here. And then we have u e to the negative u du. Now integrate by parts, because there's a u and an e to the negative u. It's a good example, good practice for that too. We'll assign f equals u, g prime equals e to the negative u. The derivative of u is just, there's a du here. The derivative of u is just 1, so this is just du. And g, the integral of e to the negative u, is equal to negative e to the negative u. So, there we go. We've got this stuff in there. Now we go and plug into integration by parts formula. And we get out front, there's a mu, because mu squared divided by mu is mu. And we have f times g is u, is negative u e to the negative u. And then we have minus the integral from 0 to infinity of negative e to the negative u du. The integral of negative e to the negative u du is just e to the u again, so that leaves it, and this is evaluated at 0 to infinity. This is infinity. Let's go back again. We go over here. We get mu times so that cancels here. Yeah. So that's what am I doing here? Yeah. So it's negative. So there's a negative out front the whole thing, and then we get u e to the negative u, and this is going to be plus e to the negative u. This whole thing's evaluated at 0 to infinity. So you keep track of the, I'm pausing there to make sure I keep track of the negative signs correctly. Both of these things evaluated at infinity are 0, because in the second case, e to the negative infinity is 0. In the first case, it's infinity times 1 over infinity, but this goes to 0 faster than this goes to infinity. So this limit is 0. So you can go through and do that, and you end up with negative mu. And evaluated at 0, these are both, this term is 0 evaluated at 0, the second term is 1. So you get negative mu times negative 1, which equals mu, and that gives us the expected value of the exponential distribution. Now, of course, it's mu, which is what we assumed it was in the first place, that was defined as, but it gives you a nice sense of how to actually go about computing expected values and the first moment here in a way that is hopefully clear. Okay, so that's one use of this, is to compute expected values. As in the previous case again, in the previous problem session, we can also use it to compute expected utilities, but now to compute expected utilities in continuous cases. So first we can discuss it sort of logically. And this problem, a risk-neutral individual is presented with a state-run lottery that costs $10 to play. So the lottery costs $10. The lottery produces a uniform distribution of payouts. So the payout from the lottery is distributed according to a uniform distribution from 0 to 15. And the question is, should you play the lottery? So that's the first part of it. The answer, you might guess, is no. There's two ways to do this. A fast way is to say the expected value of the lottery by looking at it is the midpoint of the distribution, that's 7.5. 7.5 is less than 10, so it won't work. We'll go through and compute it. The expected value of the lottery here is going to be the integral from 0 to 15 of 1/15 minus 0. That's the thing in front of the utility. Remember, the PDF of the uniform distribution is just 1 over beta minus alpha. This is a uniform distribution from alpha to beta. That's the PDF. And 0 outside of that range. Outside of the range between alpha and beta. So that's it. And we have x dx. So this thing is 1 over 15, the integral from 0 to 15 of x dx. That's 1 over 15, 1/2 x squared, evaluated at 0 to 15. That's going to equal 225 over 30, or as we guessed in the first place, 7.5. Since 7.5 is less than 10, you do not actually play. Okay, now what about if you then assume that the proceeds of the lottery go to education, and that the person is sufficiently altruistic, so as to assign a utility of 3 to the good feeling she gets for donating to education via the lottery? Should she play in this case? The answer is yes, she should play in this case. So, because if you get 3 more, you get a 7.5 expected value from the lottery, plus 3 for feeling good, that's 10.5, and 10.5 is greater than 10, therefore your benefit is greater than your cost, and you should play the lottery. So this is the kind of place you see this kind of activity, this kind of continuous distribution when you're dealing with continuous payoffs, or any continuous random variable in some decision theoretic problem or game theoretic problem. You integrate across that to compute an expected utility or expected value. That's it. And that covers Lecture 9. And that ends the probability part of this course. Thank you very much.